this video we'll have a look at the various graphs that you need to know for C1. We'll start off by looking at graphs of y is equal to x to the power of n. For integer powers, that means the power here is a whole number, and that whole number is something more than 1. For example, x to the power of 2, x to the power of 7, and so on. This is the graph of y is equal to x to the power of n, where n equals 2. So x squared, the graph of y is equal to x squared, a U-shaped curve going through the origin. Y is equal to x to the power of 3, x to the power of 4, x to the power of 5, x to the power of 6, x to the power of 7, x to the power of 8, x to the power of 9, x to the power of 10, and as you can see, there is a pattern here. The graphs for x to the power of an even number have this shape here, this U-shaped curve, which is symmetrical about the y-axis, and those which have a power that's odd have this shape, and this has some rotational symmetry about the origin. Odd and even functions. So the graphs that we've just looked at, those where the power was odd had this shape, and those where the power here was even had this sort of shape. These on the left are called odd functions, and there's some rotational symmetry about the origin. And these on the right are called even functions, and these have symmetry about the y-axis. So the y-axis there is like a mirror line. And there are some examples here for graphs which are odd functions, and some examples here of graphs which are even functions. Here we can see the graphs for y equals x squared and y equals x to the power of 4, and what we're seeing here is when the power increases, so the power's even, and when it increases, this U-shaped curve is flatter near the origin. The same thing is true when we look at y equals x to the power of some odd number, so x to the power of 3 and x to the power of 5. If you look at x to the power of 5, so the blue curve, it's flatter in this region compared to the red curve. Sketching quadratic curves. So if you're given an equation in this form, y is equal to ax squared, so that term has to be there, and then these two might both be there, or one of them might be there, or they both might be missing. If the coefficient of a is positive, so if it's greater than 0, you get a U-shaped curve. It doesn't have to be going through the x-axis. You might get something like this. So this one had 2 roots here, this one's got just the 1 root there, this one's got no roots. And if the coefficient of x squared is negative, so if it's less than 0, you might get a curve like this. There's 2 roots there, it's n-shaped, 1 root here, and no roots. A few examples of each type would be like this. On the left here, the coefficient of x squared is positive, so even if you multiply these two terms, you'll get x squared, and so that's 1x squared. The coefficient of x squared is positive. And for each of these, the coefficient of x squared is negative, so you have this n-shaped curve. So it's negative here at minus 2. In here, if you do x times x, that gives you x squared, so that's positive so far, but you've got this minus in front, so that gives you minus x squared. In this one here, you've got minus x times 3x to give you minus 3x squared, so that's negative. When you sketch a quadratic graph, you need to show roots, so the values of x here, and the y-intercept. Some graphs don't have roots, this one does. And then you can also show the line of symmetry and the equation for that line. So for instance, if the x coordinate here was 2 right there, then the equation of this line is x equals 2, because the x coordinate for any point on this line here will be 2. The vertex is the lowest point on a U-shaped curve. So for a U-shaped curve, it's the lowest point, and if it was N-shaped, it's the highest point, like this. So typically giving the coordinates for the vertex is a good idea. This is the same thing for a N-shaped curve. So in terms of roots, you may have no roots. So I'm comparing the graphs just to the x-axis there. The y-axis is not important here when we're just looking at roots. Roots are typically where the curve crosses the x-axis or intersects or just touches the x-axis. Here we can see the curve is just touching the x-axis here. There's one root. The same thing's true here. And here we have two distinct roots. So both of them are different. I'm calling them distinct roots because sometimes for this case here we call these repeated roots, but it's the same root twice. So how do you get the same root twice? Let's say you've got a curve with the equation y is equal to x plus 3 times x plus 3, so it's a factorized form for the equation of a curve. And right here at this point and this point here, so on the x-axis the y-coordinate is 0, so you've got 0 is equal to x plus 3, x plus 3. So from this factor here, x plus 3 equals 0, x equals minus 3, and as you can see you're going to get the same thing for this one. Hence you have this repeated root, but it's the same value. And for these graphs here, let's say when again y is 0 at these points, so 0 is equal to, let's say, x plus 2, x minus 3. So from here we have x is equal to minus 2, and from here we have x is equal to 3. As you can see, we have two distinct roots, two unique roots, as opposed to two repeated roots here. When we are told to sketch curves, what you're aiming to do is what you see in the right hand side here, just showing key values on the x and the y axis. What we're not doing is showing every value for x and y on the scale here, on the axes here, and we're not going to come up with some table of values for x is this and y is that in pairs, and then plot them and then join them with a smooth curve. Perhaps you did that in high school, but for A-level maths we're not plotting points and joining the points together with a smooth curve. What we're doing is sketching. The steps to follow to sketch a quadratic curve: if you put y equals 0 into the equation of the curve, so that's everywhere on the x-axis, you can solve the equation to get x values or roots. You might find there's two roots, there's one root, or there are no roots, so there's no solution to that equation when you try and solve it. To get the y-intercept, x is equal to 0 everywhere on the y-axis. So substitute in x equals 0 into the equation of the curve, and that will give you the y-intercept. And the line of symmetry is typically in the it's the midpoint of the roots. And if you have no roots, then use the completed square form for the equation of the curve, and from there you can work out the line of symmetry quite easily. And the vertex, if you substitute in the value of x that you've got for the line of symmetry, so for instance, let's say the equation of your line of symmetry was x is equal to 2. If you substitute in x equals 2 into the equation of the curve, you'll get the y-coordinate for the vertex. So the x-coordinate here in this example is 2, and then that'll give you the y-coordinate. So if you try and sketch y equals x squared plus x minus 6, so put in y equals 0, this is to work out the roots. This is the factorized form for the same equation of the curve. There's y equals 0. We have two roots, x equals 2, x equals minus 3 from each of these two factors. So we can plot, just mark 2 points on our graph. So what's the y-intercept? Equation of the curve, put in x equals 0, y is minus 6, so now we've got this point here, so we know that the graph goes through this point here. The general shape will be U-shaped because the coefficient of x squared right there is 1x squared. Going back to this, if you look at the roots, halfway between these two roots is not the y-axis. Halfway between the roots is around here. So when you sketch the curve, the U-shaped curve, if you try and do something like this, so this is the bottom of the curve and then the graph's coming up again like this, that's now wrong. The vertex should not be on the y-axis. The vertex should have been here, slightly to the left of the y-axis, halfway between these two roots, so roughly here. This is the actual graph, and as you can see, the vertex is not on the y-axis, it's to the left, it's right here. So I've got the line of symmetry, or the axis of symmetry, marked here, and the equation for this symmetry line here, it's a vertical line, so it's x is equal to something. So what's the x value here? It's the midpoint of these two roots, which is x is equal to minus a half. If you do minus 3 plus 2, that gives you minus 1, and then divide that by 2 gives you minus a half. That's how you work out the midpoint. Add the x values together and then divide by 2. That's halfway between those two. For the vertex, I know the x value is minus a half. If I substitute that into this equation, so if I put x here and here, I can get the y-coordinate for the vertex, and it turns out the y-coordinate is minus 25 over 4, or minus 6 1/4. So this is the vertex, the coordinates for the vertex. You do get a lot of fractions in the C1 paper. It's a non-calculator paper, so make sure that you brush up on your skills to do with fractions. So here is the vertex then, right there, and its coordinates for the vertex. A few examples of where you would lose marks if you were to sketch graphs like this. In this one here, it appears as though the graph here is going vertically straight up. It's not. This graph here, y equals x squared, it should be going through the origin. Clearly you can see a gap there, so that's wrong. This graph here is another familiar graph, y equals 1 over x. The problem is, if you look at the curve here, it should be going down, going towards the x-axis. It's going towards the x-axis, and then it starts to go up again. This is the part that's wrong. So that will cost you marks if you sketch something like this. Cubic functions. So anything that takes this form, ax cubed plus bx squared plus cx plus d. The only term there that definitely has to be there for this to be a cubic function is this one here. Whether all of these terms are here or some are here and some are not, it doesn't really matter. That one has to be there for a cubic function. So you may find there's only one root. You may find two roots, or you may find 1, 2, 3 roots. The shape of the graph, well, if you look at the general equation, y is equal to ax cubed plus whatever, that's the key term there. If the coefficient of the x cubed term is greater than 0, so if it's positive, so for instance y is equal to 2x cubed plus whatever other terms there are there, then the general shape, and the x-axis is not even really important here, I can get rid of that. That's the general shape. So coming from the left towards the right, the graph increases to a maximum there, decreases, and then increases again. And if the coefficient of x cubed is negative, so y is equal to minus x cubed plus whatever, so a negative coefficient of the x cubed term, again the graph from the left to the right, the graph comes down first to a minimum, increases to a maximum, and then goes down again. This is very useful to know when you're sketching cubic graphs. Okay, so we're going to sketch this cubic graph. How do we know it's cubic? Well, x times x times x will give you x cubed. Let's work out the y-intercept. So when x is equal to 0, so if I put x equals 0 in all of these, substitute that in. So you're left with 2 there, the minus 1 there, and the minus 3 because the x's are zeros. You get y equals 6. So that's the y-intercept. So what are the roots? To work out the roots, so we're looking on the x-axis here, so y equals 0. So now we've got from this factor here, x is minus 2, from this one, x equals 1, and then here, x equals 3. What will the shape of the graph be? Well, the coefficient of x cubed is positive, so it will take that kind of shape. So draw some axes, marking the key values there. So these were the roots, minus 2, 1 and 3, and the y-intercept which was 6, and we want to try and fit this curve to these points. And this is the graph that we get, something similar to this. Okay, moving on. Sketching graphs of the form y is equal to x to the power of n, where n, the power there, is some negative whole number, a negative integer. So for instance this, y equals x to the power of minus 2, that's a negative integer, which is the same as 1 over x squared. Or y equals x to the power of minus 4, which is 1 over x to the power of 4. So these values here, these numbers are even, and this is the sort of graph that you get. This is the general shape. In this graph, the curve here is going up towards the y-axis but never reaches it, which means the y-axis is an asymptote marked with this dotted line, which doesn't show up too well because it's coinciding with the y-axis. And likewise down here, the graph is going towards the x-axis but never reaches it, so it keeps getting closer and closer to the x-axis, but make sure the curve doesn't touch the x-axis or the y-axis. The x-axis is also an asymptote. Okay, so an asymptote is marked by using a dotted line, and it represents a line towards which the curve is going towards, but never reaches it. So the curve must not touch these asymptote lines. And if the power here is odd, so if you have like x to the power of minus 1 or x to the power of minus 3, then you have this sort of shape here. You've probably seen that before, and this time again you have asymptotes here and here. Okay, moving on. Any idea what this graph is? It's the graph of y is equal to the square root of x. That's a standard graph that you need to memorize, as well as all the others.